CLion a cross-platform IDE for C and C++. Download now.
Welcome to C++ Coroutines, Gods from the Machine. We'll unpack that title in a moment. Actually, let's get to my title slide. So, yeah, thank you for coming. I'm Phil Nash. I'm sure some of you know me, at least. I've got this side hustle running the conference on the event management side, but I also do talks, and that's why you're here. In fact, I also do training, and this material I'm going to show this morning is actually part of the the morning of my Coroutines training, but a bit condensed. We don't send you off to do exercises, you'll be pleased to know, but it's the same material. And in fact, this morning, actually all day today in this room, we're going to be talking about coroutines. It's a hot topic right now. C++20, of course, is brand new. It's only been around for 5 years. So we are starting to catch up. People are actually getting on to C++20 or skipping over to 23, and that'll be relevant a little bit later, and starting to get interested in maybe trying out coroutines. And of course, the big problem with coroutines is there's a really steep learning curve to get into it. Once you're in, it's not quite so bad, and hopefully we'll get glimpses of that this morning. Now, this is not my first coroutines talk, even at this conference. It's the first one this week, but gave a coroutines talk a couple of years ago here, and that one was a bit more experimental, and I'll have to say I don't think it quite worked. I was trying to actually match the problem that I had to the complexity of coroutines themselves, so it was a bit more compelling, but that just made it really difficult to get into. So this is a complete reversal of that. We're going to start from absolutely no knowledge at all and try to get you to a point where you think, yes, I know coroutines, as if you've just woken up out of the matrix. That's the aim today. Okay. First of all, this title, Gods from the Machine. If you read my abstract, you have a better idea of where I'm coming from with this. You probably know the phrase deus ex machina, Latin phrase, actually from Greek theatre originally, and then it was Latinized. Gods from the machine. The idea being that often a complicated plot was resolved towards the end by something, often a god or monster or something, being lowered in on a crane machine, same derivation. And it's like something that you didn't know about before that point. It just had to get introduced into the plot. So this sort of works on two levels. One is what I'm going to try and do is reduce the number of things you just have to know up front about coroutines in order to understand them. So that's the gods from the machine, the deus ex machinas. We keep those to a minimum, and everything else try to be sort of structured in the way that we can just sort of page fault the information in. The other way is there is a lot of machinery involved with coroutines that's sort of hidden from us, as if it's like magic being provided to us by the gods. So we are going to get a glimpse of those gods behind the machine to mix some metaphors. In fact, talking of mixing metaphors, I'm going to continue the tradition this week of having most of my images generated by ChatGPT, so be forewarned there. I mentioned this deus ex machina, but actually there's a few metaphors I'm going to use for this approach. I'm going to make it a bit of a detective story. We're going to start off with, what is a coroutine? How do they work? How do we use them in C++? And we're going to have a conversation with the compiler to try to work that out. So that's the detective story. Mention where the deus ex machinas come in. We're also going to use a bit of a TDD approach. So I said at the start, before we started, there's no testing, and that's true, but the spirit of TDD still survives in this material. We're going to start by writing code and then the code to make that work. That's the TDD approach. And we're going to keep things sort of minimal and grow them from there. So that's where that comes in. That's why we're going to start with a minimal, viable coroutine and build a little bit on that. So let's get started on that. Now, I do also want to say all of the examples we're going to look at today are highly simplified, so we can just focus on the mechanics of coroutines themselves. As I say, they're the opposite of my previous approach. But it is still going to be a lot of code. That is the nature of coroutines. So to minimize scrolling and typing, going to forego sort of lots of things like, encapsulation, and going to be missing consts and context spreads and things like that. Don't let that bother you. Put those in where necessary. We'll talk about some of the necessary ones. Okay, deus ex machinas. This is how we're going to do this, with the help of the gods. And I'm going to need that help because these are my my notes for my code examples. It came out a lot more when I printed it than I was expecting. But let's see how this goes. We are going to switch to Compiler Explorer. Who's familiar with Compiler Explorer? People didn't put their hands up. That's interesting. Okay. All right. Online compiler. I'm sure all of you know, actually. This gives us an opportunity to see how this plays out in two compilers here, GCC and Clang. So I've got GCC at the top, Clang at the bottom. We're going to be watching what error or what messages they produce. I've minimized the other part down the bottom. We just want to see when things have compiled. We're going to start, as I say, from an absolutely blank slate. This is a hello coroutine world. And what we want to do is say, okay, first of all, we can write normal functions, something like this. Right, this is what I'm going to call the least interesting function. It does nothing, it returns nothing, but it compiles, and you can call it. In fact, let's just do that. We don't need that anymore. There we go, that's compiled. As I say, very uninteresting, but it is our starting point. Remember, this is like the TDD approach, baby steps. What we're going to do is make this into a coroutine. Now, this is our first, and perhaps biggest, deus ex machina, the thing that you just have to know. You can't sort of figure this out. And the rule is, a function is a coroutine if and only if it contains one of the three co-underscore keywords. Got co-await, co-yield, and co-return. And co-return being the simplest is where we're going to start. So I'm not going to dig into what these keywords actually do just yet. I just want to note that this makes this function a coroutine, and we're going to revisit that point. Seems like a simple one, but it's easy to overlook. So I'm going to really drill it in. So this is the coroutine because of that co-underscore keyword. Now, I didn't say it's a working coroutine. You can see the error messages here. Some similarities, but differences as well. I'm finding in general that, as is often the case, Clang has the better error messages. So if you're following this example along, stick with Clang overall, but it's useful to compare them. Let's just move this over here a bit. So let's see what it's actually telling us. As I say, we don't know anything about coroutines at this point, except about the co-underscore keywords making that a coroutine. So we're going to have a look at this and see what it tells us. It says that coroutines requires a traits template. Can't find stood coroutine traits. And then it's pointing at co-return. Okay, not that helpful. The next bit, though, note, perhaps hash include coroutine is missing. Okay, that may be a little bit more useful. And could compare that to Clang, also talking about stood coroutine traits, but then include coroutine before defining a coroutine. So it's agreed we have defined a coroutine, but we need to include the coroutine header first. So let's do that. So if you don't really remember what the coroutine header is, compiler helpfully tells us. How often does it do that? That's quite nice. All right. Messages have changed. GCC says, unable to find a promise type for this coroutine. Okay, that's useful information. What's the promise type, though? Well, Clang, again, gives us a little bit more, maybe slightly more detail. It says that it has no member named promise type. But again, it's talking about coroutine traits. Now, we're not ready to talk about coroutine traits yet. We don't actually need them just yet. But it's a little unfortunate that both compilers jump straight to that. But we may not get to that in this session. So I'm going to introduce another sort of partial deus ex machina and say what we actually want to return is something that in general we call the coroutine return object. For now, we're going to call it a task type, because that's often what we think of. We'll see later how that's not quite German enough, but that'll do for now. Right, our coroutine is going to return a task. A task is a thing we're going to interact with, and we'll definitely dig into that in a bit, so don't worry if that doesn't make sense just yet. So now it's telling us unknown type name task, of course. But this bit has no member promise type, actually applies to our task. So let's define a task. And again, we're doing sort of the spirit of TDD, just an empty type there. Let's see if it gives us a bit more. Yeah, still telling us unable to find promise type for this coroutine, but it's now pointing at task. So let's try and put a promise type, and Clang gave us the spelling into task. Okay, we don't need to know what any of these mean just yet. So now it's giving us some different messages. Okay, we're getting somewhere. Right. And GCC is telling us almost everything up front. It's a bit overwhelming, and this is what we sort of want to avoid with this approach. We want to take things a step at a time and not be overwhelmed by everything we have to implement. So pretend you haven't seen that. Focus on Clang. Right. Two things, initial suspend and return void. Return void seems like the simpler one, so we'll get started on that. So it's the minimum thing we can implement to try to make this pass. So the method, return void, and Clang's happy with that. That's good. That was easy. This is going to be easy. Great. Right, we've still got initial suspend though. Okay, let's try that one next. I'll put this one above. So same approach. Minimum thing, just to introduce that symbol. Initial suspend, empty body. See what that does. Okay, not quite so simple then, right? But it's pointing at a void. Void is not a structure or union. Call to initial suspend implicitly required by the initial suspend point. That's telling us a bit about what this is used for. Makes sense given the name. There's an initial suspend point. Well, we'll look at what that is in a minute. Function is a coroutine due to the use of coreturn here, where we discuss that. Okay, a waitable type void is not a structure. That's a little bit more confusing. So this is our third deus ex machina. I'm just going to have to tell you what to do here. This is a partial one because actually, once we know a bit more about what's going on here, this will make more sense and be a bit more relatable. But for now, I'm just going to tell you that we need to return one of stood, suspend, always, or stood, suspend, never. And let's go with never. So we need to actually return an instance of that. Let's move that over, see if we can see the whole thing. There we go. Okay, that's good. We can do this one of two ways. We do this a lot, so it's worth just pausing here and mentioning this. We can name the type here and just return an empty instance, or we can use auto and instantiate the type there. Obviously, it means the same thing. I tend to prefer this style just because I got all my autos lining up, but you do you. That's fine. That passes that particular test, if we want to call it that now. Final suspend. Okay, that sounds very similar. Let's just try the same approach. I'm going to take a bigger jump here and just make a copy, change that to final suspend, and not quite. So it's Clang telling us must be declared with no except. Okay, that's easy enough. No except. Oops. And that seems to be happy with that. Okay, so final suspend needs to be no except. We are also returning stood suspend never. Now, as we're going to come on to explain why a bit later, for now, and I'm just going to tell you, you should almost always return suspend always for final suspend. And we'll make that into a catchy acronym in a bit. So unless you know otherwise, return stood suspend always. You do have to spell it correctly. It will tell you if you don't, which is good. Notice how much help we are getting from the compiler here. That this is what makes this approach work. very often with C++, if you don't get things right, it will compile or do something different and it just won't work the way you expect. And it's a lot of work to get to that point of just getting something working. And while this is a lot of work, the compiler is guiding us actually quite nicely. All right, but we're not quite there yet. Right now we're starting to get down to, well, Clang's telling us about get return object, GCC, get return object, but also unhandled exception. I'm going to pick that one this time because that one's a little bit simpler to talk about, mostly because we're not really going to dig into it. But let's just make it work. Unhandled exception, empty body. And that's happy with that. In fact, we can leave it at that. And we're not going to dig into it too much, so I'll just mention in passing, as you probably can guess, this will get called if an exception is not handled by your coroutine. We'll end up in here. Notice it doesn't take an exception type. You'll have to call stood current exception to get an exception pointer. So if you want to do error handling with coroutines, you've got to write this sort of bit of code in between to make that work. Give it whatever semantics you want. That's going to be something for an exercise left to the listener. You'll often see in demos that it will just do stood abort here. We're basically saying, well, we're not actually expecting an exception to get called here, but if it does, just abort and let us know. So we'll stick with that convention. That's all I'm going to say about unhandled exceptions. So we're now left with get return object. That's good that this one is left till last, because this is probably the more complex of these methods to get started with, but we'll try the TDD approach and just put in an empty function and give that a moment. If you know to speak to make Compiler Explorer faster, do let me know. Now that's interesting. GCC is actually happy with that. It thinks we're done at this point. Clang not so much. Well, it's mostly warnings, but we have an error. No viable conversion from return value of type void to function return type task. Now, I'm actually quite sure who's right. I know there was some debate on the committee about what should happen at this point, and we're not going to get into that today. But I think I tend to side more with Clang here, that this is not quite correct. So what do we actually need to do? Well, let's have a look at that message again and see what we can get out of it. So no viable conversion from returned value of type void, or we just wrote a void here, so it's probably that, to function return type task. Well, we know that one is down here. There's some connection between these two. It's trying to convert the void to the task. Okay, that sort of makes sense. It's called get return object, and task is our return object, and we're returning void. So that must be that we have to return task here. And it's slightly more loose than that, but that will get us out of trouble. That means we have to create a task, and we can do, actually just that will do for now. That should, I've been doing too much Rust recently. There we go. Let the Compiler Explorer elves finish. There we go. Compiler, Clang and GCC both agree. This is a valid coroutine. And it runs. And just like our first example with our normal function, it doesn't do anything. It's the least useful coroutine. But I think it's still useful that we have actually managed to, as you can see, there's a fair bit of code there to do nothing. But it is all necessary. And yeah, we don't understand it all yet. We can make some guesses at some of it. But the big problem with coroutines is this is our starting point, our baseline. Having to understand all of that up front is actually quite a lot. So just relying on the compiler to get there is quite a big help. All right, now we've got here, what else can we do? What else can we dig at, continue our detective work? So, all right. It does nothing, but is that really the case? Because it turns out there's a few ways to do nothing here. And what we're going to find working with coroutines, even once we get beyond the basics, is it's really useful to do logging. Printf debugging still rules in the world of coroutines. Now, it's changing over time, but for now, I'm going to get prepared to start doing, well, start with cout. I'll just write this out here and see what happens. So this is in our F coroutine. You can see it's printed out. So we do actually execute this code. Why is that surprising? Well, if we say here, instead of suspend never, suspend always. And there's a few ways to spell that. Only one of them is correct. All right. Wait for that to compile. The F goes away. So that controls whether our code even executes. And if we think about that a bit, let's move that over there so we can see it all. That makes sense. Initial suspend. Does our coroutine start in an initially suspended state or not? If it should always suspend initially, then we start our coroutine in a suspended state. It doesn't execute until we ask it to. And we haven't done anything like that yet. So it doesn't run. If we say suspend never, then it never starts in a suspended state, and therefore it runs eagerly, at least to the first suspension point. And we do have a suspension point here. We haven't talked about those yet, but co-return is a suspension point, as are all of the co__ keywords. We'll dig into that a little bit later. But we're starting to piece together a little bit of understanding about what happens here. Okay, now we could also put some couts in main. Well, let's start doing that. We probably want to see, whether that actually comes out as well. So I'm going to do this. Remember to escape the backslash and wait for that a moment. There we go. So it's going in and out of main. So it is actually continuing after the coroutine, even though we've got suspend always there. So we'll come back to what that really means later. So that's good to know. Now, let's say you're going to do this a lot, particularly finding out whether things sort of go in and out of certain functions. So writing std_cout everywhere gets a bit tedious. So I usually write a little helper class. I'm sure you've written this sort of thing before to trace that. And I think somewhere I got it here. Some code I wrote earlier. Don't worry if you can't read that. I didn't change the font. What I'm going to do, though, is just grab the GitHub link. Don't know why Matt's laughing. Who knew that you could do this? Include a URL from GitHub straight into Compiler Explorer. Very handy for this sort of thing.
Complete hack.
Right. Now we can do, what do they call it? Log F. I'll put the log F macro there and there. And wait for that. There we go. Now it automatically writes out the name of the function on input and exit, and it's also indenting it as well, so that turns out to be useful. So quite a handy little utility, nothing much to it, but you can grab that. I'll put a link in the Discord later if you want. All right, so now we can see what's going on, and I need to remember what I was meant to be talking about next. So, oh yeah. We can actually put now some log Fs in here as well. I'm starting to stretch the whole one-line strategy, but I do want to reduce scrolling, so just so we can see what's actually being called.
Missed the top one.
Missed the what, sorry? Top one. Well, we know that's being called because we're returning, but yeah, no, fair point. Let's put that in as well. Okay, now you can see the indentation at work. So we're in main, we go into initial suspend. We come out. Notice we haven't gone into final suspend. We'll find out why in a bit. But then we come out and we come out of main. Okay, so we're starting to get an idea of what's happening when. So while this is the least useful coroutine, it is actually still useful. It's actually teaching us something about what's going on. If I did actually throw an exception here, Yeah, I should do. Then it doesn't do anything. Okay.
Oh, because you've suspended always.
Because I've done suspend always. Thank you, yes. Let's put that back. Well spotted. That was a test. Thank you for paying attention. All right. Okay, program terminated, but we did get our unhandled exception called. Terminated, of course, because we did that stdpl. Okay, right. I think that was the end of that example, yes. So let's go back to our slides. Now we've got a taste for how we can explore the world of coroutines. And so we don't understand all of the details yet, but at least we can write one. That's a good start. So I should put that up. Yeah, there we go. I'm going to repeat this point. I think it's worth clarifying. This was our first deus ex machina. A function is a coroutine if and only if it has one of the following three keywords: co_yield, co_await, or co_return. So just now we used co_return. That's sufficient to make it a coroutine. Notice it has nothing to do with the actual return type. I'll say nothing to do. I mean, there is a relation there, but that's not what makes it a coroutine. So I can return that task from somewhere else. That's not a coroutine. Only if this function has one of those three keywords. Worth emphasizing that. And it's one of the first things we have to know. Now, we also said that initial suspend should return one of std suspend always or std suspend never. Should usually return. Now, we're going to talk a little bit later about what they actually are and when you might want to do something different. But it's usually one of those two, and it's sort of 50-50 which one, depending on what you need. As we saw, that just changes whether the coroutine starts in a suspended state or runs eagerly to the first suspension point. And similarly with final suspend. We also usually return one of those two options, but almost always it's suspend always. So by default, if you just always return suspend always from final suspend, unless you know otherwise, then you should be safe. It's almost like, well, that should probably just be the default and we should only implement it if we want something else. But this is the design we've got. All right, so these are all our deus ex machinas. Although I will say the second two I'm going to call partial deus ex machinas, because as we understand a bit more, we'll know why that's the case and we won't need to just know. A couple more partial deus ex machinas. One is task has a nested type. Now, it doesn't have to be nested, but we saw coroutine traits earlier. That's one way that we can map things differently. We're not going to get into that. To keep things simple, when you write your task type or your coroutine return type, you have a nested type in there called promise_type, spelled like that. Compiler told us how to spell it, at least Clang did. Keep it simple. That will usually work. Second one is that we didn't actually create the instance of promise type. That was created for us by the gods in the machine. And interestingly, the lifetime is tied to that of the coroutine. And we'll see why in a bit, but that's really important to know as well. In fact, if you think of it as the promise type is instantiated within whatever's holding the coroutine, which we'll look at in a bit, then that will go a long way. The reason that's important is, as we're going to see a bit later, getting the information in and out of the coroutine is always via the promise type. So knowing where that's stored is really useful. In fact, let's dig into that a little bit. First of all, quick test. What makes this a coroutine? Well done, you were paying attention. All right. Yeah, the presence of the co_return keyword. I'm going to skip the underscore. The co-return keyword. If we had co_await or co_yield, that would also make it a coroutine. It's not the task return. And of course, we call it like this. So far, we haven't actually used our return value in our demo. We'll do that next. But that's what you would usually do. What's interesting here is that this is going to look a bit odd if you've not seen coroutines before. What we're returning with our co-return is nothing to do with what we're returning from F. Right, they're two different returns. It's a little bit confusing at first. So what do we actually get when we say auto task? Well, we get our task, of course. So where does the co-return go? Remember, there was a function on our promise type where we did return void. As you can probably guess, if you return a function, it calls something called return value. So it goes into the promise type. But we'll see this next. So how does this work then? We're returning one thing and getting another thing returned. Well, again, this is gods in the machine, implementation details. For exposition purposes only, this is not what actually happens, but it's just a way to think about it. By no means complete. The compiler is generating something like this, and a bit more, as we'll see. So what we actually wrote as our body is just the initial block, but that may or may not get executed straight away. And this is why we can potentially defer it. And that's well, in this case, it's a function on this thing we're calling coroutine frame. See, our promise type is in there. So the promise type is part of the coroutine frame. So is our initial block. If there are other blocks later after suspension points, they'll also be there. Any local variables that span suspension points, that will become more obvious later, become member variables of this coroutine frame. So they persist across calls. But then the coroutine frame gets instantiated or gets allocated on the stack, on the heap, sorry. See the new keyword there. Worth pointing this out. Let's say that's not actually what happens, but it's a good exposition. A lot of people get stuck on this and think, oh, I can't afford a heap allocation here. Coroutines are not for me. My code's on the, performance sensitive path. You hear that a lot. Coroutines are too slow. And it's all because of the heap allocation. Well, first of all, I question most of the time whether that's really a problem. There are ways to avoid that heap allocation. We're not going to get into it today, but just so you know, there's something called the heap allocation elision optimization, or HALO. Very fragile, unfortunately, not particularly reliable, but that will often kick in and save that anyway. But if you really, really need to make sure that doesn't get allocated on the heap, there are slightly unergonomic ways to add allocator support. That's why we're not going to deal with it today, but just so you're aware, you can do that. So usually by default, allocated on the heap. Think of it that way. That's the right mental model. There are some ways to avoid it. Okay. Once we've got the coroutine frame, from the frame you can get to the promise, and it just calls get return object on there. That's what gets returned. That's how this pieces together. As I say, this is a long way from what actually happens. Just to add a bit more in, and you can see how it's already getting quite complex. So we'll stop with this, but actually once we've got the return object, before we do return it, we need to see whether we should initially suspend. Now, if you've looked at coroutines before at all, you'll know that this line here, comparing against to suspend never, is complete nonsense. That can never work. It's just a mental model for now. When we look later at what suspend never and suspend always actually are, you'll see what we need to do instead. But we're just asking the promise type, should we initially suspend? And if not, we'll call our initial block here. Otherwise, we can get called later. And there's also stuff to do with if an exception is thrown at this point, that's going to call for unhandled exception, things like that. There's more to it, but this may help to understand how these things work together, but you don't actually need to internalize this, don't worry. Let's put some of this into pictures. Right? Describe this thing a few different ways. So pictures may help. We're going to build this up as we go, but what I want to start with is pointing out there are some things that the compiler or the standard library provides on the right-hand side, and there are things that we need to provide. So you see we need to write this promise type. We always need to write a promise type. A lot of methods in there. Individually, they're actually quite straightforward. It's just remembering them all and how they interact. That's why relying on the compiler to tell us can be really useful. That's usually nested inside what Been calling the task type, more generally the coroutine return object type. Those things we write ourselves, but we don't instantiate the promise type. As we saw, that's handled for us, allocated as part of the coroutine frame. We never see the coroutine frame. It's completely opaque to us, so don't worry about it. But we do need to interact with it. We'll see how we do that in a bit. But two other things we have seen that are provided by the standard library, these two types, suspend always and suspend never, very useful types. Very simple types, but very useful. All right, we'll come back to this. Let's come back to our deus ex machinas. Here's a new one. We can control and destroy coroutines, coroutine frames, through a coroutine handle. So I said the coroutine frame itself is completely opaque. We never see it. We interact with it using a handle. How do we get the handle? We can get a coroutine handle from a promise object, and also, confusingly, vice versa. So how do you get a promise object? You get it from the coroutine handle. How do you get the coroutine handle? We get it from the promise object. Right, we've got to break the deadlock somewhere. Well, you remember in get return object, we are actually in the promise type. Right, we have the promise type. We can get a handle from that, and we will do next. So remember that. But let's just put that on our picture. So coroutine handle provided by the standard library. From there, you can get to a promise type. And I should have made that arrow two-way, but you get the idea. Usually, we'll pass that coroutine handle onto our task object. We haven't done that yet. We'll do that next. So that it can hold on to it and it can interact with and manage the lifetime of the coroutine. Now, this is important. You would think, here we are in 2020, and this should be some sort of RAII type. Manage the lifetime of the coroutine for us. But the thing is, there's different ways that you might want to manage it. So there is no one way that it should work. So the coroutine handle doesn't do lifetime or resource management. You've got to do that. It's got a destroy method. That needs to be built into our task type. So let's have a look at how this works now with our next demo. Right. We come back to where we were. So we've got our promise type in our task. What I'm going to do is just, okay, we'll make it private. I'm going to add stood coroutine handle. And it's a template that takes the promise type. Okay, now our task has a coroutine handle. All right, but how do we actually give that an initial value? So remember we said it's all to do with this get return object. That's the thing that's creating the task. So what we can do is here, we can say, and we'll have to spell it out again. I should have done copy and paste. It is from promise, isn't it? Yeah. And we are the promise type, so I'm going to do star this. And that should oh yeah. Let's take that out.
Yeah.
I did say we'll leave encapsulation out of this, but there we go. We've still got that exception. No, we haven't. Yes, we have. We'll make that unexceptional again. There we go. Catching up. Okay. All right, so that hasn't
Question,
really changed much. We have a question, yes.
could I ask why initial suspend has no accept, but final suspend does?
So why final suspend has no accept, but initial suspend doesn't need it? It's because the point that final suspend is invoked, you may not actually have any opportunity to interact with it at that point. So we need to make sure that there's not an exception that propagates. Whereas with initial suspend, we have a suspended coroutine, we can interact with it and get the exception out. Of course, you can make initial suspend no except, you're just not required to do so for the purpose of making it work as a coroutine. So, yeah, thanks for the question. Okay.
When you had your exception earlier, I noticed that the signal that's getting thrown is segment violation, not abort, whereas you're aborting. Any particular reason why?
It's just so that we can skip it for the purpose of,
Okay,
of the
right.
talk. Yeah, no, I'm not saying it's not important. I've actually done 3 completely different talks now on error handling. This is something I consider important. I think it deserves a bit more time than I can spend today. So I'm going to follow the honoured tradition of leaving error handling as an exercise for now. All right, so where were we? We have, let's try to make this a bit more visible. We've changed our getReturn object to pass a coroutine handle to our task. And we got that from the promise type. So that's how we connect that up. So now we have a coroutine handle. And we can now add a destructor to task that calls handle.destroy. That should work, yeah. In fact, if I just comment that out again. Interesting. So would have expected final expend not to be printed there. Sorry?
Yeah, when you first put it in, I was surprised that final suspend was being called.
Yeah. Okay. Okay. Not sure I can debug that right now, but without calling handle.destroy, the coroutine frame is just going to carry on living in a suspended state. So actually, yeah, getting ahead of myself. Yeah, final suspend is called, and it's returned suspend always. So the coroutine remains in a suspended state until we call .destroy on the handle. So can we log in the destructor? That's, yeah. No, we can't. Not with this destructor, because the coroutine itself is run to completion. That's why we called final suspend, but now it's just sitting there, sort of invisibly in memory, in a suspended state, waiting for us to actually clean it up. What I can show you, though, is that if we now change final suspend to suspend never, now we get a 6F, because we're getting a double deletion effectively. By making it suspend never, the coroutine is cleaning itself up. Saying, at the end of final suspend, I'm going to clean myself up. We're not in a suspended state, we're just gone. So now when we call handle.destroy, it's already destroyed at that point. Sam, yes? Oh, hold on, wait for the mic.
Where is handle initialized?
Where is
Handle initialized.
handle initialized?
That's
Yeah, so that was what I added here.
okay, yeah, I missed it.
So we passed to the task constructor, coroutine handle from promise. So this is one of the magic functions that, given a promise instance, will actually give you a coroutine handle.
But the handle member itself, the name,
Sorry?
a handle could have a different name, right? So where is it?
Handle with a different name. No, so this is the task constructor. So we're getting coroutine handle from promise and passing it to task constructor. We don't have an explicit constructor, so
That's why
directly initialized.
I was missing the
Yeah, sorry.
link.
Again,
Okay.
saving some lines of code here. So relying on all the shortcuts. Sorry about that. Hopefully that makes sense. Right, but yeah, what I wanted to point out was that we do have to be careful about resource management here. We are responsible for cleaning up that coroutine unless we have told it to clean itself up. But the reason that we say we should always have suspend always here is because if at the end of the coroutine it's cleaned itself up, we can no longer interact with it. And we haven't done it yet, but in the moment we're going to get co-return to return something. We're going to put that in the promise type, and we can't get it out because it's gone. So usually we want to do that resource management. Now we can also do, and usually should, say if our handle actually is pointing at something, then destroy. That doesn't help us with the final suspend problem though, because that's not going to set our handle. But that's just good management. All right, so let's change this now to return something or co-return something. So no member named return value. I said that would come up. So let's change this to return value. Just see that get called for now. Okay, great. And there we go, return value with int. So this promise type, this is our interface, incoming interface. This is what the coroutine machinery is called, and that's why we've sort of built it out by the compiler messages. Notice it's not a sort of a virtual function-based interface. It's more of a concept-based interface. So that means that things like value categories and precise types we can be a little bit looser with. So here, anything that can take an int would make this signature work, for example. So just to see that, there we go. Different value categories, take it by const reference, by value, whatever we need to make our semantics work. But we're just going to take that in as an integer. But how are we going to see that outside of the coroutine? So that is going to be the responsibility of our task wrapper. So I'm going to say get return value. Now, how can I get to that? But we haven't done anything with it. So let's comment that out for a moment. And I'm going to say promise type has a member called returned value. I'll leave it uninitialized. Don't worry for a moment. You passed the test again. You're really sharp today. Great. It's actually quite useful. So, return value was value. So we've now stored it at least. How can we get to it so that we can return it from our task? So let's uncomment this. Should really do that as well. Okay. So remember I said, given a handle, we can go the other way. And we can say handle.promise gets us to our promise object. And from there, because everything is public, and usually you would leave this public to be fair, we can get to our returned value. Yes, I did that right. So just to prove that, we never actually did write this, did we? We can do good cout. Actually, no, I think I've got log. Task got get returned value. Should print that. Review this in a moment just to see working. There we go. There's our 42 as our final answer. Right. So let's just review what we did there. It's pretty straightforward, but it's because we've got so many things involved that we may not be familiar with. It's just worth seeing how this all hangs together, because this is really the core of how we interact with coroutines. Everything sort of goes via the promise type. That's our incoming and outgoing interface, in a sense. So the coroutine machinery, when you get to the co-return, is calling return value with that value. It's then up to us to remember that, store it as our returned value member in this case. We could put it somewhere else. We might want to put it in a global or whatever. Usually it's going to be a local variable. And then in our task, or whatever we're using to wrap our promise type, the thing that the coroutine returns, we can add some method to access it, some sort of getter, usually. And we get to the promise object from the handle by saying handle.promise, and then there we can get to, in this case, our return value. And we'll see this pattern a lot. And it goes the other way as well. We'll get onto that. Does that make sense? Any questions on this? Because I think this is an essential point to internalize at this point. Okay. Yeah. Sorry, Will.
So just to clarify, all of the other local variables in the coroutine function, those are stored for us, but it's just the return value we need to bookkeep ourselves.
Yes, and that's actually quite a good point. So if you remember earlier, we looked at the exposition code that said we've got a coroutine frame with the promise type instantiated in it, and also said that any variables that live across the suspension point are stored as members of the coroutine frame. They may not actually be members, but they are stored in the coroutine frame, which means we could actually return or yield, as we'll see, references or pointers to those things, and they will still be alive outside. Now, to be careful, but it is actually quite common to do that. You don't have to copy large amounts of data from the coroutine code into the promise type because they're all alive at the same time anyway.
You have to make sure those references don't outlive the coroutine once it's been destroyed.
Sorry, I missed that.
You need to make sure that those references to those local variables don't outlive the coroutine.
Right. The key is, though, that the promise type lives as long as the coroutine frame.
Oh.
So anything that's in the coroutine frame has the same lifetime anyway.
Oh.
So in general, it won't matter. Obviously, specific cases it might. But we're not going to get into that too much, so I thought worth mentioning it now since you brought that up. Thank you.
Thanks.
Okay. Interestingly, again, we're not going to dig into it, but probably worth asking the question of maybe not that satisfying having an uninitialized variable there. We're all interested in safety in C++ these days. Think of ways you might want to mitigate against that. There's a few ways at runtime, maybe even some compile time opportunities, but we'll talk about that afterwards. I think there was another question. Was that answered? Still valid? Yeah, Peter.
There's a question online. There's a question online.
Okay, well, take the online one first and then
Okay.
maybe Peter.
The question is, why can't we store a promise object directly inside the task? Why do we need to continue?
Sorry,
Why do we need continue handle for this?
Can you repeat once more? Sorry.
Okay.
So why can't we store a promise object directly inside a task? Why do we need coroutine handle for this?
Right. Sorry. Thank you. Yeah. So why do we go handle.promise and not just store the promise type somewhere? We can do. We need to store the handle anyway for lifetime management. We could also store a pointer or reference to the promise type, but that's what handle has anyway. In practice, I found it's not actually any overhead doing it this way, maybe slight syntactic overhead. I've tried a few different ways. I just keep coming back to this as being sort of the simplest, most idiomatic way. But you can experiment with that. You're absolutely right. We could hold on to it. The other thing to bear in mind is that we haven't added any lifetime semantics to task itself right now. Usually, you want to make them, at the very least, non-copyable. You may want them to be movable. So at most, there'll be move-only types. You only ever want one task managing your coroutine at a time. There are some weird edge cases. You might want a shared task. We definitely don't want to get into that. But if you have a move-only task, it's nice and simple to move the handle around. And maybe if you have a pointer to the promise, you could do that as well. References become a bit more awkward. So just bear that in mind. Peter, do you still have a question?
So about the gets returned value function, is the name somehow restricted, or can I have multiple of those?
No, it's a good question. So get return value here. It's entirely up to us. So we can call it get return value for Peter, if we want.
Oh, thanks a lot.
And just for you, it still works. So yeah, that's a great point because it illustrates something I was going to come and talk about next, which is the task type. It's entirely up to us to define our interface to what our coroutine does, or what our type of coroutine does. Because you can reuse these things. We're doing a lot of work right now, maybe reusable. In fact, we're going to see a good example of that coming up. But this is our chance to define, to some extent, the semantics and definitely the interface to our coroutine. Taking the low-level stuff that the promise type of the handle gives us and wrapping it up in something that's a bit of a nicer abstraction. So entirely up to us. Thank you. Okay, we're going to have to move on because I think we're already over on this.
Got another question online?
Okay, one more.
Does the F0 function get executed in the main thread by default, or does its execution get deferred to another thread?
Good question, and it's very often comes up. There's an assumption beforehand that coroutines have something to do with threading. They don't. They're completely orthogonal. You can mix them, and that's actually quite good. And if you have been to any of the senders receivers talks, you'll know that that's a really good way of mixing threads and coroutines for something that's actually quite easy and safer to use. But coroutines themselves don't provide any threading. That's something you have to bake in. And I think we probably won't get to that example that I did have as like bonus material, unfortunately. Come to my workshop, I will cover it there. But you can schedule a coroutine to resume on another thread, but you have to do that work. Or use something like the senders receivers framework in C++26 or one of the third-party libraries that support the same sort of thing. I think Boostazio also has good coroutine support, so if you want something a little bit more old school, that's also available. Thanks for that question. But yes, as I say, we do need to move on. Do just want to say, and I mentioned this in passing, but we want to usually disable copies, and unless we want to do the work to make it work, even moves. So quick way to do this is, make sure I do this right. If we just write a move assignment operator and delete it. This is on our task type. Did I get that right? There we go. That is sufficient to make this a non-movable, non-copyable object. A nice little shortcut. I think Peter Summerlad calls it the rule of des demover. You have to see his talks to understand why. I'm not going to go into that right now. Nice little shortcut that makes this non-copyable and non-movable, which we can verify. If we try to take a copy of it. There we go. And it's worth doing that and having like a reflex to do that, because we're having to do our resource management ourselves here. And you know how easy it is to get double deletes or that sort of thing. You can also, and it's actually not that hard to do, I've got some example code, wrap the coroutine handle in like a movable handle or a non-movable handle. And that can just make that a bit easier. That then follows the rule of 0, definitely recommended. I've also done a talk on that. Okay, let's move on. So we've got the return type out. I think I've got through all of that. Let's go back to our slides. Went back too far. There we go. Here's that catchy acronym. RZFS. Right. Almost always suspend always from final suspend. Just rolls off the tongue. Yeah. Now, It's a bit of a joke, but on the other hand, once you've seen this, it does actually start to come naturally. Yeah, almost always, suspend always from final suspend. And now we've sort of explained a little bit about why. It's to do with that resource management. So we want to clean up, usually, the coroutine, because if we don't do that, we won't be able to get that return value or anything at the end of the lifetime of the coroutine. It will just be cleaned up from under our feet. We'll still be holding our coroutine handle, and it's gone. Right. We only want to do that in case we know that's exactly what we want to do. And that's usually to do with those cases where we have resumed the coroutine on another thread, for example. And we want that to clean up when it's done. It will be pushing work to us rather than us actually interacting with it along the way. So almost always, suspend always from final suspend. Remember that catchy acronym. Okay. So, okay. I think we did that one. Let's rough that. Yeah, I jumped ahead. Okay. So let us move on to the next interesting keyword. So returning values is not that interesting. We could already do that. And we could even do it in a deferred execution model using lambdas. So really, this is the first time actually being a coroutine becomes useful. The co_yield keyword, co-yield. This is a suspension point, as is co-return, but a resumable one now. This is what makes it a coroutine. We can resume them again. And we can get values out just like with co-return. So let's go back to our code demo. And what we're going to do, we're going to continue returning a value for Peter. But now we're also going to co-yield a value. If we didn't co-return anything, this will still be a coroutine because it's got the __ keyword. Right, but this doesn't compile. So let's see what that tells us. Taking a bit longer. All right, GCC is done. No member name to yield value. So that's what we need to add to our promise type now. So we're just continuing what we were doing before. So yield value, and exactly the same as before. In this case, it's an integer, but it's up to us what we actually put there that accepts the integer. So I'll just put the log in there for now. What did I miss? Oh, I know what I missed. So yield value does actually return something. And what it returns is, again, deus ex machina. I just had to tell you this for now, is what's an awaiter. We haven't talked about that yet. Usually one of, or usually, in fact, suspend always. So what we're saying here is, when you get to co-yield, should we actually suspend here and return control to the caller, or can we actually just carry on? Sometimes that's actually the right thing to do. Usually, again, almost always, suspend always from yield value as well. All right. Notice our return value has gone away now, because what's happened is, where are we? Here we go. When we've done co-yield, our coroutine has suspended at this point. We haven't actually got to the return value, so we're going to need to somehow tell the coroutine to resume. But that's not going to work because, again, we control the task class task type. So we need to write resume. But how do we do that? Well, as you can probably imagine, there is a method on handle, which happens to be called resume, which will resume the coroutine. Hopefully, yeah, I got that right. Okay, so we're not actually doing anything with the yielded value yet, but you can see we have got our return value back. So we are back where we thought we should be. we have yielded, we've got a value, but we haven't done anything with it. But this is just the same situation we had with co-return. So we can now add yielded value. And everything we've said about co-return applies here. And yeah, apologies for these one-line functions. Otherwise, just too much scrolling. So we've got the yielded value into the promise type, and let's copy and paste this time. So get yielded value. We'll do it for Peter again. Why not? So get yielded value for Peter. And now we can say here, get yielded value for Peter. Hope you appreciate everything I'm doing for you, Peter.
Yeah, thanks.
Oh, there we go. So to catch up. All right. Well, you see the 1 in the output. We still got our 42. It's worth checking these things because you can see how easy it is to get out of sync. Now, what we're doing here with these yields is not really what you're going to be doing when you do use co-yield. Usually it's a little bit more structured than this. I'm just trying to build up into that just to show you how the pieces fit together. So don't worry too much, but we do need to pay attention to when things happen because we're responsible for both sides of this. Right. But we can also yield again. And you'll see that return value will go away again for the same reason, but we can just do that again. And you can see where this is going. Every time we add a yield, well, we've got to do a resume on the other side. It's not very scalable writing out longhand like this. So we're probably going to want to write some sort of loop. To write a loop, we also want to know when the loop ends. And so far, we're just been doing it by counting. There's 2 yields, so we have 2 resumes. Again, not very scalable. So our resume method, what if that returned the Boolean to say whether the coroutine is done, which we could check by, sorry, it's not Rust, by calling handle.done. So handle.done asks the coroutine, are you done? Or do you have more code to execute? And you can write that as a separate function. I'm just combining them here. It's quite often done that way. Now, and this is the bit I always get wrong if I try to do it from memory. So I'm going to try and find my example to get the loop right. I can't seem to find for the moment. Okay, I might have to do this on the fly. All right, let's give this a go. So I think we do while. No, we don't. Do. I know last time I tried to do this in front of an audience, it didn't work. So just to warn you, don't need those. Yeah, so we do have it off by 1. So I've lost the return value. So I think we might need to do that somewhere else. Just for the sake of getting this moving, let's assume I got that right. But it does illustrate that it's quite tricky to get this right. It's not rocket science. And you try a few things, oh yeah, I just need to do it in this order, and then it all works. So you can do it, but you do need to pay attention and maybe do a lot of testing. But there's actually a better way. And what I'm going to do is suspend that example for a moment, go back to our slides. Didn't put that up again. And I'll just show you this is where I was going to go. I'm going to put a few more co-yields in. You can see the pattern emerging. And no good example complete without the Fibonacci sequence. So this is our coroutine code. We've got co-yields in there. I've got rid of the co-return, cluttering up at this point. And in our calling code, we're getting our coroutine, which has a promise type with the yield value. And when we do yield, calls yield value, stores it, and then does a suspend. And that's what I should have written. So we did actually need to start with the resume. That's right, because we needed to start in a suspended state. Too late. All right. And then we can do our loop, get our yielded values, and when we're done, we drop out the bottom. Hopefully that makes more sense now on my prepared slide. Right, but we're not done there, because then we get the yielded value out. We saw that part. When we resume, we go back and continue on in our coroutine, go to the next co-yield, and come back again for all of our co-yields. So you can think of this as like an unrolled loop at this point. And usually we're going to write an actual loop here. But you can write sort of these naked co-yields like this. But there is a sort of a loop going on both sides. Hopefully you can see that. So I want to take a moment to look at something. We started off with this title slide. And one of the reasons I chose this ChatGPT varied version of Van Gogh's Starry Night is because Coroutines has always reminded me of this pattern. You know, these swirls we've got going on here. If we sort of overlay that a bit, you can sort of see there's the loop. And I can see the recognition in Matt's face there. But let's go down the rabbit hole a little bit more, because so I've got ChatGPT to generate this. So I thought, well, let's go a bit further. That's not quite right. So I asked it to produce a painting in the style of Van Gogh's Starry Night, but depicting a binary pulsar, because that's really what we've got going on here. And after a couple of refinement prompts, this is what it actually came up with, and I quite like that. Let's put that in there. So now you can see we've got one loop going on up here, one loop going on down here, and the values are just sort of swirling around them like this. Yeah, you see that? Or the execution. That's quite a nice visualization. And I think that's really appropriate. But we've got generative AI to generate an image of what we actually call generators. I know, it was worth it, wasn't it? This is a really common reusable pattern with coroutines. Co-yield in a loop and an outer loop in our calling code. Getting values, resuming, and then checking whether we're done. But this part, the getting values, resuming, and checking if we're done, not unique to coroutines. We've been doing this for a long time. It's basis of iterators, ranges, and even before that, it's basically how we implement loops in general. So given that we do control that task interface, why can't we just put an iterator interface on that? And that's going to make things easier to work with. And having done that, we realized that that code generalizes really nicely. The only part we really need to parameterize, in most cases, is going to be the type that we're actually iterating over. So C++23 finally got std generator, which does exactly that. So we spent, 70 minutes or so getting to this point. This is all the work we have to do to make generators work. Let's see what it looks like if we actually have C++23. So go back to our example. Did I have? No, it's not that one. Okay. I think what we need to do, let's get rid of GCC and just make this C++23. And let's get rid of all of that. And make this std generator of int. Get that co-return. And then we can say for I'm actually going to do this directly here. Sorry, Peter. What did I miss? Doesn't like that. Hmm? Yes, we do. You're right. Thank you. There is another header we need to include for the generator template itself. And there we go. So, okay, imagine that's the full Fibonacci sequence. In fact, maybe let's see if I can just very quickly get that in, because this is actually quite nice. I'm not really going to talk through this. This is not a session on how to implement a Fibonacci generator, so I'm just going to copy from here so I get it right. We need to co-yield the initial implementation. I'll learn to spell one day. And we can use stood exchange. If you've not used stood exchange, by the way, you should really learn it. It really simplifies a lot of common tasks. Is that complaining about? Do I? No, that's right. Okay. Hmm? Oh, yeah. Thanks, cplusplus. It's okay. There we go. So what you notice about this is it doesn't actually end. So that's obviously just going to keep generating. Well, I mean, it will stop working after a while, but yeah, we probably want to limit that. Sorry? Not start with, oh, yeah. Okay, ignore the 0. Again, this is not a tutorial on the Fibonacci sequence, so what I do want to show you, though, is that now we've got a generator, we actually have a range, so we can do, let's make sure I get the syntax right again. Yeah. We can just use take. We'll do that afterwards, don't we? Let's take the first 10. Yeah, because that was on the previous page, wasn't it? No, I don't have it. No? Okay. Yeah, I think I might have just picked it up. So yeah, you probably do need to include something for that, but there we go. So we'd take the first 10 generated values, and that will work for any generator, as will pretty much all of the ranges. So when does the generator interface get destroyed? So I believe that is a move only. If you're not 100% sure, I think it's a move only type. But don't quote me on that. I'll need to check. I don't have that off the top of my head, but that will make sense, I think. Which means that it will, in its destructor, destroy the underlying coroutine. So it's doing a lot of work for us. In fact, beyond the simple stuff, it handles apparently recursive generators as well, which was something that, one of the main reasons it actually didn't make C++20, they were still getting that bit right, but it is at least in C++23. So I know a lot of people who have been moving on from C++17, they've been thinking, should we actually go to 20 or should we just go straight to 23? If you want to use coroutines, go to 23 because this is so much nicer. But if you do end up on C++20, at least use some third-party polyfill library. Because how much of that coroutine code that we've been working on all morning do you see here? Pretty much none of it. Using coroutines is actually quite nice, at least with generators. The don't think we're going to get onto much to do with awaiters. I'm just going to start on it. Awaiters are much more general and complex, and we don't have library support for that yet. But there is a stood task, which is an async task that works with senders receivers, coming in C++26. I think it actually got adopted in just in time. So that's something to look forward to, but it's a way off yet. So we're still going to have to work on the low-level code for now. So let's see if we can actually get on to just introducing awaiters. But just do want to take a moment to step back and just review what we talked about. Because we covered quite a lot of ground, actually. You know this bit now. Co_ keyword is what makes it a coroutine, nothing else. We have to implement the promise type, which means implementing all of the first 5 methods, and usually some of the last 3. So let's just take those one at a time. The return object is how we get the thing that actually gets returned from the coroutine function. We've been talking about tasks, but also std generator. That comes from here. See it constructed there. Strictly speaking, it only has to return something that can be converted to that type, but that's just a little detail. We will usually see this form getting the promise type, getting the handle from the promise type, which is us here, passing that onto the task. Don't always need that. Usually you do. Then initial suspend, what happens when your coroutine starts? Does it start in a suspended state or not? We'll just look at that very briefly in a moment, a bit more detail. So it could be suspend always or suspend never. Final suspend should almost always, remember the catchy acronym, almost always suspend always from final suspend, because that's what allows us to clean it up afterwards. Unless you know you want the coroutine to clean itself up, always return suspend always. Unhandled exception, we're leaving that as an exercise. Yield value gets called if you co-yield a value, makes sense. Again, you get control of value categories and type conversions and things. Only need to implement that if co-yield is used. We need one of return void or return value. Interestingly, in the case of return value, they can actually return different types at different points in the coroutine. So it's a little bit different to just the standard return keyword in a normal function. But you can't mix return void and return value. But there is a bit of a foot gun here. While the compiler will usually tell us when we haven't implemented one of these required methods, if you don't have a co-return, just like a normal function, you can drop off the end and there's an implicit co-return. But an implicit co-return doesn't require you to implement return void. And if you run off the end of a function and you haven't implemented it, that's undefined behavior. It's one of the new ways we've managed to introduce undefined behavior in. Yes, we're still doing it. And I think the reason for that is more or less to do with generators. We saw that Fibonacci generator. It actually never returns. It just goes on forever until you suspend it and destroy the coroutine. So we didn't actually need to implement return void or return value for that. So I think that's the reason that it's there, but it does mean there's a bit of a foot gun there. Okay. So we talked a bit about the coroutine interface type or the coroutine return type. The thing that the coroutine returns that we implement, that's our interface to the coroutine. We are responsible for implementing that. Sometimes we call it a task, call it a generator if it's a generator. It could be something else. You can actually map that to existing types. It's a bit of an advanced topic we won't cover today. You can even just return a handle, but that's usually too low level. Point is, we control that. And it's this level of control that we have that makes this so complicated. So many different options. But if you stick to the usually do this, you can get quite far. Okay, now I'm saying this again now because we've looked at co-yield, we've looked at co-return, we haven't looked at co-await. We have 4 minutes to cover awaiters. Ready? We're not going to go deep, but I do want to at least introduce them because we sort of foreshadowed them a bit. Let's at least get through this bit because we have these two concepts, awaiters and awaitables. And knowing that these two are different things can be quite confusing. So it's not actually necessary to really know what the difference is or be able to internalize that. It's a little bit like there's a difference between parameters and arguments. If you don't remember what the difference is, it doesn't really matter. The same sort of thing here. But an awaiter is a thing with a specific interface that gets called when you use the co-await keyword. An awaitable is something that you can call co-await on, so it's able to be awaited. Okay, that might help. And that might be an awaiter, because all awaiters are awaitables, but it might be something that can get converted to an awaiter. That's the difference. So just knowing that those two concepts exist is the main thing. If you don't remember which is which, it doesn't matter too much. Now, we also have trivially awaitable types. Now, while they are trivially awaitable, they are awaiters. So a little bit confusing again. I think I've just got time to show you that I'm going to use C-line this time. The reason I'm going to use C-line is because if you're using an IDE, you can use it to navigate to the implementation. So if we look at what stood suspend always actually is, and you can see we've got stood suspend never as well. These are trivial awaitables, trivially awaitable types. So they are awaiters. And you can see an awaiter is something that has these three member functions: await ready, await suspend, and await resume. Await ready is the only thing that varies between these two. Suspend never, await ready returns true. Suspend always, await ready returns false. So you can sort of get an idea of what our await ready actually does. It says, is this thing already ready? In which case we don't need to suspend. Yeah, so if await ready returns true, we don't suspend never, and vice versa. Pretty straightforward. The other two are a little bit more involved, and unfortunately, I think we're going to be out of time to even start on those. But they're what happens when the coroutine actually gets suspended, and there's some options there. You get a coroutine handle. An await resume does get called when you resume, but perhaps more importantly, if you return something back to the coroutine, that will come through await resume. So if you do co-await on something, that's an await expression when you return something. So sorry we didn't get onto that, but at least wanted to show you. You can actually go and look in the source code easily enough and think, oh yeah, that's the three methods. And we can also use that compiler-driven approach. So I'm just going to go back to the slides. Skip over the last demos. Oops. And yeah, usually they should all be context per constant, except where they can be. Usually they can. I'm going to whiz through this. This is going to look complex, but I will put the slides up and you can go back and look at it later. This is just the control flow. What happens when you call co-await on something? So we talked about await ready. If you return true, it just resumes, goes back again. So it's a shortcut, but if it's false, it actually suspends the coroutine. So there's some overhead to that. Calls await suspend, and then there's a few different ways to come out of that, which we don't have time to cover. But if you return false, then it still doesn't go back to the caller, resumes again. If you return true or void, then it actually returns back to the caller. And we won't talk about the other one with the handle, but you can resume another coroutine, which is also known as symmetric transfer. But that pretty much is the whole control flow map of awaiters. It looks complex on one slide, but if you follow each individual path, it's actually fairly manageable. The complex bit is the three different signatures that you can have for await suspend. But when you actually get onto that, hopefully this will help to disentangle it. And I think we're going to have to finish there. So I'm going to skip ahead Yeah, I was a bit ambitious with this. Can I? Oh, there it is. If I go here. Yeah, just to remind you about generators. Use the generator if you have it available. And I think we can get to the final suspend. So thank you very much. If you have questions, see me afterwards. Thank you.